All right. So this is on page 16. Just be careful because for some reason it photocopied page 17, then page 16. So clearly something happened there. So this one says a battery is run through a solution of potassium chloride, determine what is oxidized and reduced in the half reaction. Okay. So this is not an electroplating situation. And so for this one, we have an electrolytic solution. Okay. All right. So let's get this set up here. So we have got a battery plus, okay, this is my anode. And the anode isn't, by the way, always on the left. It's just kind of by convention, I do that. Cathode doesn't have to be. This is our wire coming down, some sort of electrode, right? Some graphite or something. All right, we have in solution potassium ions, not potassium, but the ions, chloride, the ions, and we have water. All right, so at the anode, which is where oxidation takes place, we have two possible reactions. We could either have the chloride oxidized or water. And the anode is a little bit tricky because remember, when you look for it on the sheet, it's going to be flipped over from what you expect. All right, so we've got Cl minus. This is going to go to Cl2, so I've got to go back and add this 2 in, plus 2 electrons. Oh boy, I'm really going to run out of room here. That's a plus 2. Okay, that is a 2. All right, and my value for this one is negative 3, 6. Okay, and then my other one is going to be water. So that's H. Oops. Okay. 2H2O goes to oxygen gas because at the anode, oxygen gas is formed from water. H plus, which is acid, which you wouldn't see unless you had an indicator, but then it would turn red. And then 4 electrons. Oh, and it's 4 of these H pluses. Go back. All right, and this one's negative 1.23. So out of these two, the water is going to happen. Okay, because it has the higher value. It takes less energy to do it. And we're going to come over here to the cathode. So at the cathode, we have reduction. And our two possible reactions over here are the potassium ions. And then again, hey, we've got water. So potassium is K plus an electron gives us K. And I'm looking at a slightly different sheet, but it might be rounded just a tiny bit different, but it's around 2.93 volts. And then water. Now we got to be careful because this one, water does not generate oxygen gas if it occurs. It generates, picks up 2 electrons, 2 waters, and it generates hydrogen gas and 2 OH minuses. And I'm sort of out of room here. This is negative 0.828. So out of these two, the water will happen. Okay, so in this case, we have the waters occurring at both. So what we should see here is we should see bubbles. And at the anode, these are oxygen, right? And floating around in solution, that's an O2. Floating around in solution, we would have hydrogen ions around there. I don't really have room to write that. On this side, at the cathode, we would also have bubbles, and that would be H2. Okay, a whole bunch of bubbles. All right. So if I wanted to add these two reactions together, I would need to multiply this reaction by 2 because here I have 2 electrons and here I have 4. So this would become 4, 4, 2, and 4. And then we can add them together. I don't really have room here, but you would just add the reactant side and then the product side. And in the overall net reaction, you do not have any, you don't show the electrons. Okay, so now we have everything labeled. The overall E cell value we can calculate. So we would have E cell would be, right that over here, would be negative 1.23, and I'm getting that value right here, plus negative 0.828, and this is somewhere around 2.0 something. Let's see, 1.23. There's a decimal there. I just can't really see it. And 0.828. Okay, so this is equal to negative 2.058 or 2.06 if we're going with 3 sig figs. Volts is the units. Okay, and we could also do Gibbs by doing negative NFE. Okay, so if we wanted to do that. Okay, so I'm going to actually clear this, and if you get confused, you could always come back to the screen by just using the reverse button, but I need space to be able to work. So I'm going to delete this. Okay, and you should have this written down on the top of your paper if you need to go back to it. So if we read part A below, it says if 1.5 amps, okay, are run for 15 minutes. So let's start labeling. So let's see. Determine the volume of oxygen gas which is produced at the anode. Okay. All right. And the temperature is 20 degrees C and the pressure is 0.99. So we're definitely dealing with a gas here. So we know, oh boy, we're going to need pivnert. Okay. And we always know with these type of problems, we're going to need stoichiometry because I'm going to convert charge, which is based on electrons, into oxygen gas. And I'm going to use those half reactions that we just determined to do that. Okay, so I have I in this case, which is 1.5 amps. I also have time, but I need to get it into seconds. So I'm going to have to take the 15 minutes and multiply that by 60. And that will give us 900 seconds. Okay. Well, if I have I and I have T, I can plug this in and solve for Q because Q is going to be able to tell me moles of electrons. So whenever you are doing these problems, Q is your gateway to be able to get between the balanced chemical equation and the current and the time and the electrochemistry piece to it. Okay. Just in this case, what's different is with pivnert, you just have an equation. With molarity, it's moles over liters. Okay. With other things, you're just using either a constant or you're using an equation, one or the other. In this case, you have to use both a constant and an equation. That's kind of the tricky part. So, but we will figure this out. So we have 1.5. Q is what we're solving for because that's going to give us moles of electrons. And time is 900. And we have the charge is 1350, and that's coulombs. They tell us the units on the equation sheet, which really, really helps. All right, so now we're going to take that. Okay, so we're starting with 1350 coulombs, and coulombs are going to be able to relate charge to moles of electrons. We use that with Faraday's constant. In this problem, we've got to put Faraday's constant on the bottom because I need coulombs to cancel out, and I need to get into the unit of moles of electrons. So we have 96485 coulombs. 1 mole. You can't just write 1 mole. It has to be 1 mole of electrons, right? Because that's the label. Okay, so now I have moles of electrons out of coulombs, and I'm going to look at my half reaction. Well, there are 4 moles of electrons. I'm getting this from my half reaction at the anode because that's where oxygen gas is formed per 1 mole of O2. Okay, and I want to leave it in moles this time. I don't want to go to grams because if it's a gas, I'm going to need to pivnert to get the volume. So moles of electrons cancels, and I'm in moles of oxygen. So now it's just a matter of plugging this into the calculator. And that gives me 0.00. So you might want to put this in scientific notation. 3, 4. Oh, it's 9, 7. So this would be 5, 0 moles of O2. Okay, so now if I want to get volume, switch colors again here. We're going to plug this into PivNert because this is a gas, right? We can only use PivNert for gases. Pressure is 0.99. Volume is what we're solving for. N is what we just found. I'm going to run out of room. We kind of go sideways here. 0.0821. And temperature is 2. Okay, I've seen the problem. 2, it should be 293 because it has to be in Kelvin. We know that. All right, so now we just need to plug this in. So we have 0.0035 times 0.0821 times 293 divided by 0.99. And we get 0.50 liters, which would be 85 milliliters. Okay, so again, in this problem, we could have also solved for, if we knew the volume, we could have solved for the concentration of H+. We could have solved for the concentration of OH-. Since they're in solution, it makes most sense to put them into concentrations. You could solve for the volume of hydrogen gas. Okay, so you could solve for, once you know the moles of electrons, once you know one thing in this stoichiometric reaction, once you know one value, you know the moles of everything else. And then from there, we can just do different conversions to get it into the type of substance that we want. Okay, thank you.